So the three momentum equations that are in Eulerian fluid mechanics are called the Navier-Stokes equations. So here they are, the Navier-Stokes equations, all three of them. So you have the, oops, I left out one term here, minus g rho. So x momentum, rho du dt, u du dx, v du dy, w du dz equals minus dp dx mu del squared u. Notice that y and x are basically identical equations. We've just replaced all the numerators with v, so instead of u. So dv dt instead of du dt, dv dx instead of du dx, dv dy instead of du dy, etc. But notice that these terms do not. These terms stay. These are what's being carried in the x direction, carried in the y direction, carried in the z direction. So they stay with their derivatives. So it's u with x, v with y, w with z. All these things become v. Of course, we change to the y pressure gradient and del squared v. Same thing in z. We have w's, of course, in the numerator all the way across. U stays with x, v stays with d dy, w stays with d by dz. Pressure gradient in z now, del squared w. And if gravity is in the z direction, we have a body force term. So there's the body force term at the end. That's saying that gravity is going to tend to pull things downward in the z direction, assuming z is pointed in the upward direction. They are often written by dividing by rho, so you're going to see a lot of that. So I will rewrite them all with rho divided, and they're kind of silly in a way. You could do it, but we'll do it anyway. So we have, of course, just du dt plus u du dx plus v du dy plus w du dz equals minus 1 over rho dp dx, because the rho came out. But in the next term, we actually go to nu. And so this is where that kinematic viscosity that we learned about earlier when we were studying viscosity, we said there's going to be a kinematic viscosity that we use, and that's this. So that's your kinematic viscosity. And nu is defined as mu divided by rho. So that's why that's an important variable or important quantity. It's made up specifically so that it shows up in this form in these Navier-Stokes equations. dv dt, I have the x, y momentum equation, u dv dx plus v dv dy plus w dv dz equals minus 1 over rho dp dy plus nu, the kinematic viscosity, del squared v, and finally z momentum, dw dt plus u dw dx plus v dw dy plus w dw dz equals minus 1 over rho dp dz plus nu del squared w minus g, because we've now divided by rho, so that g just sits out there by itself. Notice that we have 4 unknowns here. 4 unknowns, u, v, w, and p are unknowns. Gravity is known. Viscosity is a property of the fluid. Rho is considered to be constant because we said it was incompressible flow. So remember, our equation of state for incompressible flow is just rho is constant. We have to figure out what it is. The fourth equation we need to solve these 4 unknowns, we have 3 equations, is mass conservation. So for incompressible flow, we have du dx plus dv dy plus dw dz is equal to 0. So that's the fourth equation. This is all for incompressible flow. One thing you can notice right away, even if you're not really familiar with how you're going to solve these, this equation seems to basically be about u. So you can imagine trying to find u using x momentum equation. This equation is about v. You can imagine trying to find v using the y momentum equation. And this equation is about z. So you can imagine trying to find, or about w, you can imagine trying to find w using the z momentum equation. And that would mean you try to find p using this equation. Well, there's a problem with finding p using that equation because there is no p in that equation. So this is a real problem. It's a challenge to solve these equations. for a lot of reasons, but that's one of them. There's not really a P equation. In addition, these are nonlinear partial differential equations. You have u's multiplying u's. They're strongly coupled together. As you can see, I need to find u, and then I use u down here, and I use u down here. I need v, and I need v here and v here. So they all are very strongly coupled with each other. They all depend on each other, so they have to be all solved really simultaneously. It's a very difficult set of equations to solve, but we will see that even without a computer, we can learn an awful lot in certain circumstances, and in certain circumstances, even solve problems exactly using these Navier-Stokes equations.